All right, today we're tackling a huge question, one that really gets to the core of why people are so nervous about nuclear power. You know the image I'm talking about, right? It's everywhere in movies and TV, the mushroom cloud right next to the cooling tower. But is that real? Can the same thing that makes electricity for your home also go off like an atomic bomb? Well, let's get into it. And look, it's easy to see why we make that connection. I mean, the words nuclear reactor and nuclear weapon sound almost the same. And that's been feeding our fears for, what, decades now. But to really get to the truth, we've got to push past that feeling and look at the actual science behind it. So let's start at the beginning. Before we can even talk about whether a reactor can act like a bomb, we have to ask a more basic question. What is an explosion? Like, what's actually happening when something goes bang? Okay, so here's the deal. An explosion is all about one thing: speed. It's a super, super fast release of energy. A great example is lightning. You've got this jolt of electricity that heats up the air almost instantly. That air expands like crazy, violently, faster than sound. And that creates a shockwave. You know what we call that shockwave? Thunder. So the key takeaway here is extremely rapid. And now let's look at the opposite. Imagine you're heating water in a tank, but you've got a little valve open. The steam just hisses out, right? Slowly, gradually. Yeah, you could inflate a balloon with it, but there's no shockwave, no bang. It's the same amount of energy, really, but it's released over a much longer time. And that's the point. No speed, no explosion. Simple as that. Okay, but then you have dynamite. A detonator sets off a chemical reaction that just rips through that whole stit in a blink of an eye. That incredibly fast energy release is what creates the massive, destructive shockwave we think of as an explosion. So you see, the big lesson here isn't about how much energy you have, it's about how fast you can let it all out at once. All right, so now we have our key principle. Speed is everything. With that in mind, let's finally compare the two things we're here to talk about, the reactor and the bomb. And right here, this is the absolute core of it. The whole point of a nuclear reactor is to release energy slowly and steadily, under control over years and years. A nuclear bomb, its entire reason for being is the exact opposite. It's designed to dump all its energy, completely uncontrolled, in a fraction of a second. They are literally built to be polar opposites. And the reason they're so different, well, it all starts with the most basic thing, the fuel. It turns out the stuff you put in a reactor is completely different from the stuff you put in a bomb. So in your typical power plant reactor, the fuel is only about 3 to 5% of the special stuff that can actually cause a reaction, uranium-235. The other 95% is a different kind of uranium that actually slows things down. It gets in the way. It's kind of like trying to start a bonfire with really, really damp logs. Yeah, you can get it to smolder and burn slowly, but there is just no way it's going to erupt into a raging inferno. A bomb, though, totally different story. It needs fuel that's over 90% pure uranium-235. So if the reactor fuel is damp wood, this is like taking a bone-dry log and soaking it in gasoline. The material is so pure, so ready to go, that a chain reaction can just rip through it almost instantly. And that is what gives you a nuclear explosion. There's another great way to think about this. It's like the difference between the engine in your car and a napalm bomb. I mean, they both use gasoline, right? But you don't get in your car every morning worried it's a ticking time bomb. Why? Because the engine is built for a slow, controlled burn, while the bomb is built for a sudden, catastrophic one. Same basic fuel source, but the machines are designed for completely opposite jobs. Okay, this brings us to a word that honestly just freaks people out: critical. You hear on the news, the reactor has gone critical, and it sounds like it's about to blow, right? But in the world of nuclear physics, critical just means stable. It's actually the perfect, boring, steady state you want it to be in. It just means the chain reaction is sustaining itself perfectly. It's the goal, not the emergency. All right, but I know what you're thinking. What about Chernobyl? If these things can't explode like a bomb, then what in the world happened there? It's a fair question. So let's look at the actual physics of that disaster. And here's the absolute most important thing to understand. The explosion at Chernobyl was a steam explosion and then a hydrogen explosion. It was absolutely catastrophic, don't get me wrong, but it was not a nuclear explosion. The physics of what happened are totally different. So here's the play-by-play. They were running a safety test that was, well, it was badly designed and they made some terrible mistakes. This caused a massive, uncontrolled power surge. That surge basically acted like a giant kettle element, instantly boiling all the cooling water into steam. The pressure was so immense, it literally blew the 1,000-ton lid right off the top of the reactor. At its heart, it was a gigantic, tragic boiler explosion. Yeah, the heat came from a nuclear reaction, but the bang itself was from steam and chemicals. And it's really important to say the nuclear industry learned a ton from accidents like that. Modern reactor designs, especially the new small modular reactors, or SMRs, are a whole different ballgame. They're built with what's called passive safety. That means they use the basic laws of physics, things like gravity and natural heat circulation, to shut themselves down automatically if something goes wrong. No power needed, no person has to flip a switch. They're literally designed to fail safe. Okay, so let's tie this all together. Let's do a quick recap of the hard, scientific reasons why a power plant just can't go off like a bomb. There are basically 3 non-negotiable physical roadblocks. Number 1, the fuel is just not pure enough. It's that damp wood problem we talked about. It just won't explode. Number 2, there's no trigger mechanism. A bomb has a whole complicated system to kick things off, and a reactor has absolutely nothing like that. And number 3, reactors have a built-in safety brake. Because of their physics, the hotter they get, the worse they are at continuing the reaction. So they automatically start to slow themselves down. And look, this isn't just my opinion or some industry talking point. This is one of the very, very few things that scientists in this field will say with absolute certainty. You almost never hear scientists talk in absolutes, but on this, they do. The scientific consensus is crystal clear. A reactor cannot explode like a nuclear bomb. The laws of physics just don't allow it. So hopefully we can put that fear of a mushroom cloud coming from a power plant to bed. But that doesn't mean there are zero risks, right? The real challenges, the things engineers are focused on today, are things like managing heat after a shutdown, dealing with long-term waste, and just generally making these systems foolproof against any kind of accident, not just bomb-like ones. But you know what? That's a whole other story for another day. Thanks for joining me.